All right, so welcome back. Let's recap the method that we learned in the last example to find a basis for a span in En. You take the generators that you're given. So here we were given these generators. You place them in a matrix and you reduce. All right, so you place them in a matrix and you reduce. You're going to keep the vectors corresponding to leading entries in R. All right, so in our case here, we had two leading entries. We had these two, and so we kept the two orange vectors. Now, if you go to RREF, for 2, you could go to REF. You still know where the leading entries are. If you go to RREF, the columns give the coefficient necessary to write excluded vectors in terms of the basis vectors. All right, so that's what we learned here. This column not only tells you that the third vector is redundant, it gives you a recipe for it. It tells you that V3 is 3 half times V1 and plus minus 3 half times V2. All right, since we're talking about spans, there's a subspace that we sort of hinted at, but we never actually defined. It's called a column space. If I take A to be an M by N matrix, the column space of A is the span of V1 through Vn, where V1 through Vn are the columns of A. All right, so we link this matrix with the span of V1, Vn, because we keep using it anyways to figure out a basis, to figure out what it looks like geometrically and such. All right, so the previous method gives us a basis for the column space of any matrix. We can use a similar method to find a basis for a span in other vector space. As we did here, you start with S, and you know it gives you everything in V, and then you start removing any element of S that can be written in terms of the preceding elements. That worked in En, it's going to work everywhere else. In the next video, we'll be looking at example 1.5.7. We'll have a span of matrices and we'll try to find a basis for it.